Hello, this is Mrs. Scarpel, and in this video I'm going to walk you through a quadratic pattern converted to a table into a graph and recursive and explicit equations. I've gone ahead and created the table for this diagram. Figure 1 has 1 square, Figure 2 has 3, Figure 3 has 6 squares, and Figure 4 has 10. I've also taken the time to label my graph. This is very important. You need to label what the axes represent. You also need to have a scale, and the spacing between values needs to be equal. You need to be going in equal size steps. Now I'm using steps of 1, labeled a little differently on each axis. I numbered every single value from 0 to 8 on my horizontal axis, and I have labeled the even numbered ones on every other line. Even if I'm going to adjust my spacing after the first value, the spacing that would follow that value needs to be the same between that value and 0. So you want to make sure you always have equal spacing. So when I graph my figure number with the number of squares, 1 is 1, 2 is 3, 3 is 6, and 4 is 10. Now I can see that each time it increased a little bit more. It looks like it increased 1 more than the time before. And I can go to my table and verify that. From 1 to 3 we have an increase of 2, from 3 to 6 we have an increase of 3, from 6 to 10 we have an increase of 4. So if I wanted to find figure number 5, it would stand to reason that I would then add 5 to keep the pattern going. And 10 plus 5 is 15. I can plot that on my graph as well. The reason I'm not going to connect these points is because my data doesn't require a connection of points. The data is for specific figures. We don't have any information between figures. So we're just looking at each figure. This is a discrete situation. So we want to see separate points. We do not want to see them connected together. Now if it were a situation of time versus distance, or time versus amount of rain fallen, then we would probably want to connect our points, because the change is happening continuously over time in those cases. When it comes to a recursive equation, I'm going to use my x values, but I'm going to start with my x value of 2, followed by 3 and 4, because I want the first difference that was used to get the value for figure number 2. So to get the value for figure number 2, it was a plus 2. So that first difference for 2 was 2. To go to my third difference, it was a plus 3. So for 3, this first difference was 3. And for the fourth one, it was a plus 4. So my fourth term had a first difference of 4. Now since I have my table labeled with n's, I'm going to adjust this to be an n as well. So a recursive equation for a quadratic pattern, and I can tell you that this is quadratic because the first difference is linear, and what I mean by that is the increase from each value to the next in my first difference is the same. We call this the second difference. The second difference is constant. In this case it's a 1. So for our recursive equation, we are going to be stating the first value, so the first figure had 1 square, and then we use the notation f of n to represent the next term. And the next term, based on the previous term, because recursive is about something that keeps occurring. It's a recurring situation. So for previous, we use f of n minus 1. And then it's going to be plus something n. And we might end up with a plus constant amount on the n too. We won't know until we check it. So I'm going to put a blank n plus blank in my table, and then I'm going to do some testing. So when my n is 2, before I go to that, I know what this coefficient is in front of my n. That coefficient is the second difference. The second difference is going to lead my n term. So I'm going to take that 1 times my n value of 2, and I'm going to see how that compares to the first difference. 1 times 2 is 2, so I don't need to add anything more to that one. I could just say plus 0. I then am going to test 1 times 3. 1 times 3 is 3, so again, we don't have to add anything. It's a plus 0. I'm going to test it one more time. 1 times 4 is 4. Again, I don't have to add anything, so I'm writing a 0 there. So I know I have 1n. In my recursive equation, it's going to be previous plus 1 times n. And I don't need this plus blank, unless I needed to add something or subtract something to equal my first difference. For the explicit equation, we use the figure numbers, and I can go ahead and use 1, 2, 3, 4. I'm going to use the values of those numbers, 1, 3, 6, and 10. Now, something about quadratics is they always have a squared term. So my explicit equation is going to have f of n equals something n squared, and we could potentially have something more added behind that. We won't know for sure. Now, we've talked about the first differences being 2, 3, and 4. And then we've talked about the second difference then being a constant 1. And the coefficient that goes in front of the n squared, the value that goes in front of n squared is 1/2 of the second difference. Since our second difference was 1, half of that is 1/2. So I know I'm going to have at least an f of n equals 1/2 n squared. So up here, I'm going to be testing 1/2 n squared, and I'm going to see if I need to add anything to that. So when I test this, I'm going to have 1/2 times 1 squared. 1 squared equals 1. 1/2 of 1 is 1/2. Well, I need it to equal 1, so I would add a half to get my 1. When I test 1/2 times 2 squared, 2 squared is 4. Half of 4 is 2. Well, to get 3, I have to add 1. Test this with 1/2 times 3 squared. 3 squared is 9. Half of that is 4.5. I would have to add 1.5 to make it equal 6. 1/2 times 4 squared. 4 squared is 16. Half of that is 8. I would have to add 2 to equal 10. Now, these aren't the same constant amount. So the next thing I'm going to look at is how do those values, how does 1/2 relate to my 1? How does 1 relate to 2? How does 1.5 relate to 3? How does 2 relate to 4? What is the relationship? I know 1/2 is half of 1, and 1 is half of 2. 1.5 is half of 3, and 2 is half of 4. So I am adding half of my figure number. So I finish my explicit equation with 1/2 n. And that's my explicit equation. And I can always use a table like this to help me find it. So what can we take away from this? The graph is a parabola. And what I mean by a parabola is it is going to have a curve. A full parabola would be a U shape. In this particular pattern, we only saw part of the parabola. So you need to remember that a parabola is going to be a curve. The graph of a quadratic will be a curve. The second difference is constant. Quadratic equations have a linear rate of change. That's the first difference, increasing at a constant rate. Equations have an x squared or some variable squared. They don't have an exponent larger than 2. They always have something squared. They can be written as the product of linear expressions. So our explicit equation, if we had been looking at an area situation, I could have written it as 1/2 n times n plus 1. And if I distribute that, I have 1/2 n squared plus 1/2 n. So I would consider the 1/2 n and the n plus 1 to be linear expressions. The coefficient of the squared term is half the second difference. So the 1/2 that we have here is half of the second difference. It was half of the 1. And those are the things that we need to remember for quadratic equations, quadratic functions, quadratic patterns.